Hello everyone, move to the next experiment. So our next experiment is to control the speed of DC shunt motor using field resistance and armature resistance control. Okay, so DC speed control, basically speed control possible in DC motor. Okay, and DC motor is in DC motor we supply to the electrical power, it give a mechanical output. So this is your DC motor. In DC motor we apply the electrical power and output is mechanical power. Okay, and by definition, when a current carrying conductor placed this is a current carrying conductor placed in a is connected with a voltage source. Okay, this is your so this is your current carrying conductor placed in a magnetic field. It experiences a torque. Okay, so move to the our experimental part. So speed control in DC machine is speed control in DC shunt motor is possible by first flux means field weakening method, or next is from armature side, armature resistance by change the armature resistance or connect rheostat series with armature. Okay, and third is voltage control. Okay, so first speed control of DC shunt motor. First method is field weakening or field current. First method is field weakening or field current control. Okay, so in this method basically in speed control method, in general we write down N is directly proportional to EB and divide by 5. Okay, so basically this is a uh, EMF equation. So EB is directly proportional to N phi. Okay, so here we write N is directly proportional to EB and inversely proportional to phi from in this relation. Okay, and here we also written as EB is V minus I RA. Okay, divide by phi. So this method is used for feed feed current field current control. Okay, so in this case we decrease the value of if, decrease the value of if is decreases means phi is decreases, phi is decreases means n is inversely proportional to phi. So phi is decreases means n is increases. Okay, so in this case this method is used for when we want to rotate our DC machine rotor above the rated speed. Okay, so uh, make the connection. Okay, so connection is this is your armature terminal. So this is suppose A and double A. Okay, and this is your field winding. Field winding terminal is suppose F F double F. Okay, in between we connect a rheostat. Okay, in between we connect a rheostat. So suppose this is a one terminal of rheostat and this is a second terminal of rheostat. Okay, so second terminal of rheostat connected with this A means armature terminal A and double F connected with double A. Okay, and this machine connect with the supply voltage V. Okay, this is a motor, so this is connected with the V supply. Okay, so this is your flux is phi sh. Okay, and this is your EB. EB is your back EMF. So in this case this is ISH. ISH is means your shunt. This is your shunt. Uh, this is your shunt winding current. So this is by V divided by RSH. Okay, this is RSH. RSH divided by this terminal voltage V. So you get ISH. Okay, so in this case we find the RSH equal to V divided by, and the resistance of this rheostat is R, so this is written as RSH plus R. Okay, so here this R is variable. Okay, so in this case, 1st, 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 when we increase the value of r, value of r is increases, means your denominator is increases, denominator is increases means this ISH is decreases. Okay, this ISH is decreases means this phi sh ISH decreases means phi sh decreases, phi sh decreases means n is increases, because phi sh is inversely proportional to r, or n is inversely proportional to phi sh. So phi sh is decreases means n is increases here. Okay, so this is your rated voltage. So basically here, by connecting an external resistance in series with field winding, and by increasing it from minimum value to maximum value, the field current will be reduced. Okay, the field current is reduces, the field current is reduces, field current is reduces means flux is reduces, flux is reduces means speed is increases. Okay, the minimum speed in this method is only rated. Okay, so rated speed is minimum in this case. It is a efficient speed control method, because here we decrease the value of flux, means field is weakening, so loss associated with external resistance in the field circuit is small. Okay, so no need of large rheostat and no need of additional cooling in this method. Okay, requires a 4-point starter especially to control the speed of wide range. Okay, move, move to the simulation part. Okay, so in this method, this is your here we open the simulation. This is your MCV, and this is your 3-point starter, voltmeter, ammeter. This rheostat is used for field resistance, and this rheostat is used for armature resistance. Okay, this is your DC motor, and this is your front view of DC motor. Okay, and this is show the uh, this is your speedometer reading. Okay, so first step is, this is a and this is your B. So this is a positive terminal, this is your positive terminal of MCV. Okay, this is your okay, this is the positive terminal of MCV. Okay, so this is a positive terminal of MCV connect to this point. Okay, so this is basically in this case. Okay, so this is your starter L terminal, F terminal, and A terminal. Okay, so here suppose we make a connection, we connect this DC shunt motor uh, into the field weakening control method. So in between a field, you connect this field resistance series with this field resistance. Okay, so connection says, first this is your positive voltage, connect to this P. Okay, and make a general connection, then we make according to the instruction. So this positive terminal will connect to this L. So this positive voltage come across this F and A. So suppose you connect a field with series with this rheostat. So F connect to this field resistance terminal E, and this F connect to, suppose you want to measure the current. So this rheostat connect with series with this armature, and this ammeter connect series with this field winding. Okay, and A and F dash is short here, dotted here. Okay, and suppose here armature resistance is available, so you connect this next rheostat series with the armature winding. So this S connect with this A. Okay, and suppose you want to measure the voltage, okay, across the terminals. So connect this positive to positive and negative to negative. So this is a general connection. Okay, here here we make a connection according to the instruction. So okay, so this is your A and A dash, and F is F and F dash. Okay, so next step is, first connect this terminal to positive terminal to the this A dash. Okay, and A to Y, A to Y. Okay, so here basically we in which here we connect A and A dash and F dash is connect shunt manner. Okay, and give a positive supply according to the simulation. Okay, next step is A to, this is A, connect to this ammeter negative terminal. Okay, and after that this is a B terminal. This is a negative terminal of MCB. B connect to this is a B connect to this. B means this negative supply negative terminal of MCB connect to L. This is your L, and after that next step is this is a rheostat E terminal. Rheostat E terminal connect to this ammeter, connect to this ammeter E2 amp, and next is, this is a F terminal. F terminal is connected to this field winding series with this field winding. Okay, next step is this is a G terminal. G terminal is connected with A. Okay, so in armature armature winding we connect this armature in armature winding we place a rheostat. Okay, so this A connected with G. Okay, and this H terminal H terminal is connected with this voltmeter, and voltmeter positive terminal, and this and this basically this I means I terminal connected to this A. Okay, so here we control the voltage by this resistance. We control the voltage across the armature. Okay, and next is and this A terminal connect to this uh, H terminal, and last this is F terminal connected to this ammeter. Okay, so click on check connection. Connection is correct. Okay, so basically this is L, F and A. So here this is supply pass to L, and this F connect with a series with this ammeter, and this ammeter connect with a series rheostat, and this rheostat connect with a connect with series with this field winding. Okay, and this is a voltmeter. Okay, so our connection is correct. So turn on MCV and change the field resistance. Okay, so okay, so this is your field resistance. Okay, so here we clearly watch this reading. So suppose armature resistance is, suppose we decrease the armature resistance, sorry, armature means no, armature means field resistance. When we decrease the field resistance, and field resistance is decreases, so our arm, so our field resistance is decreases, so field current is higher. Field current is higher means flux is higher. Flux is higher means your speed is 1015 rpm. Click on add to table. So take next reading. Here we increase the value of field resistance, and we increase the value of field resistance. Field resistance is increases means your phi is decreases. Phi is decreases means speed is increases. Click on add to table, take the next reading. Okay, again we decrease the value of field resistance. Field resistance value is field resistance value is increases. Field resistance value is increases, then your IF is decreases. Okay, IF is 0.8 ampere. IF is decreases means speed is again increases. So speed is your speed is 1400 rpm. Again increase the value of field resistance, so your current is decreases, IF is decreases. IF is decreases means the speed is increases. Click on add to table. Okay, again field resistance is increases means your current is decreases. Current is decreases means your speed is increases here. Okay, take okay, take the next reading. Add to table. Okay, add to table, to table, add to table. Okay, so check the table value. Okay, so this is your observation table. Okay, current is 1, your armature speed is 1015 rpm. So when we decrease the value of IF, this is the IF value, IF is decreases, so your speed is increases, so N is increases. Okay, so next click on plot graph. This is your graph. So next method is rheostat or armature resistance control method. So in armature resistance control method, first make a circuit diagram. So this is your field winding, this is F double F. Okay, this is your F double F, and next this is your armature, armature A double A terminal, armature A and double A terminal okay, so this F and double A short here, sorted here, and next is this is a rheostat. Okay, this is your rheostat, connect with series, rheostat connect with series with this armature. Okay, so armature and second terminal of armature connect to this F. Okay, and apply voltage here. Okay, and this is your EB. Okay, so in this case, when we increase or decrease the value of resistance, voltage drop across this rheostat is increases and decreases, depends on position of jockey. So in this case, we know that EB equal to V minus IA RA. Okay, so in this case this is R, and this is the resistance of rheostat, and this is the resistance of armature. So R plus RA plus R. Okay, so in this case when we when we increase the value of this R, this R value is increases, means this total term is increases. Okay, this total term is increases means this total term is increases means this EB is decreases here. Okay, EB is decreases means we know that EB is directly proportional to, this is a phi and this is your n. So EB is directly proportional to n. So EB is decreases means n is decreases. Okay, so basically by the connecting external resistance in series with armature, the voltage across the armature is varies. Consequently the speed is varying. Okay, it is basically voltage control without varying supply voltage. Okay, so this method is basically uh, voltage control without varying a supply voltage. Okay, it's include resistance and produce more copper loss. Okay, so due to this resistance more copper loss is here, therefore this method is less efficient. If this it is used to control the speed from below the rated speed. So this method is used for when we want to uh, decrease speed below the rated speed. Okay, so here no need of requirement of 4-point starter. There is no additional armature reaction effect. Okay, it's required a cooling methods. Okay, and it is also constant torque and variable power. Okay, and the armature rheostat should be at maximum position during the starting. So this is these are the case for this method. Okay, suppose we further increase the value of R. So R is increases, so this drop is increases, this drop is increases, P minus this more drop, so this EV is decreases here. EV is decreases means EV is directly proportional to N, so N is decreases here. So this method is less efficient and more heating in this case. So this generally this method is not used. Move to the simulation part. Okay, let's start the make connection. So first is first of all connect positive terminal of MCV to negative uh, positive terminal of MCV connect to the negative terminal of voltmeter, and this positive terminal of MCV connect to A2 and F2 also. A2 and F2 also. Okay, next connect negative terminal of MCV to L. So this is negative terminal of MCV, connect to L, and L is the L port of starter. And next is connect F port of starter. Connect F port of starter to the positive terminal of ammeter. Positive terminal of ammeter. Next is connect A port of starter. Connect A port of starter to the positive terminal of armature resistance. A port of starter connect to the positive terminal of armature resistance. Okay. Next, connect positive terminal of voltmeter to negative terminal of armature resistance. Okay. So connect positive terminal of voltmeter to the negative terminal of armature resistance. Okay. And also to be port of A1. Connect to the A1. And next, connect ammeter negative terminal to the positive terminal of field resistance. Okay. Connect ammeter negative terminal to the positive terminal of field resistance. Okay. Next, connect negative terminal of field resistance to port F1. Okay, so this connect to this port F1. Okay, F1 of motor. Then connect A1 of motor. Connect A1 of motor to the negative terminal of armature resistance. And finally, connect A1 to this positive terminal of voltmeter. Okay, so here when we increase the value of armature resistance, okay, so this is the first reading, voltage 200, current is this, and click on add to table. This is the first reading, and okay, next reading is, suppose we increase the value of field armature resistance, so voltage drop is increases. So voltage drop is increases means N is decreases. Okay, click on add to table, so speed is decreases. Again, increase the value of armature resistance, voltage drop across armature is voltage drop across rheostat is increases, so voltage across uh, armature is less, so speed is also less. Further, increase the value of rheostat, so voltage drop across rheostat is increases, voltage across uh, armature is reduces, so speed is also reduces. Okay, click on add to table, take few more readings, click on add to table, again click on add to table, add to table. Okay, and this is your graph. Okay, so here clearly visible so in this case when we increase the voltage drop across the armature, so IA is in this case voltage drop means voltage this is your voltage drop, means this is your EA voltage. EA voltage is decreases, EA voltage decreases means your N is decreases. Okay, n is decreases, and this is your graph. This is your graph. Voltage, this is your voltage. Voltage is decreases, speed is also decreases. So this is your graph. So this is all about the speed control of DC motor.